Ladies and gentlemen, my name is Martin Wald and I would like to present our paper by a collective of authors from Brno University of Technology, Czech Technical University in Prague, and a software company, Ideastatica. The paper is titled Lateral-torsional buckling of a stiffened beam with semirigid joints. In the introduction, I will briefly talk about buckling analysis of members and design of joints. Then I will describe our experiment, the corresponding numerical model, and in the end I will compare the results. The new Eurocode will provide us with a fancy flowchart indicating where to use geometrically linear and nonlinear analysis and where to include global and local imperfections. The most advanced method, M5, allows to only check the strength because buckling is captured by imperfections and nonlinear analysis. In the current design procedures, the design of both members and joints is done separately, often to different load cases. Connections are most often designed as rigid or pinned to the envelope of internal forces from the global model. We do not care, for example, about the forces coming from warping of the beam due to lateral-torsional buckling. To determine buckling strength of members, we need to know the boundary conditions, and the guides are prepared only for pinned or fixed boundary conditions. One example where design of members including connections, considering their stiffness, may be beneficial is angle in a truss connected by gusset plates. We always assume that its buckling length is equal to the system length. The buckling behavior is however quite complicated. There is a shift and rotation of member axis compared to the gusset plate, and the connection has some stiffness. The design of angles, connected especially by quite stiff welded connections, bring savings. Here is an example where the connection is difficult to design on its own. The compressed member bends the gusset plate, and when the member buckles, the bending load is more significant. Designing member together with joints brings safety. This is our experiment we performed at Brno University of Technology at Atmos Center. The beam IPE 180 was connected by semirigid end plate joints to the column stubs. The beam was in some cases stiffened by welded inclined stiffeners. The member subjected to 3-point bending by a load introduced through a rod and a pin. The beam was able to rotate and move laterally freely. We had 9 specimens, 3 without stiffeners, base, 3 with stiffeners welded prior to the test, built up, and 3 with stiffeners welded under load at about 50% of load resistance, strengthened. The end plate joints were designed as semirigid around both axes. The load was introduced with an intended eccentricity of 5 mm. Unfortunately, the bolt holes were not precise but with standard tolerances, and after the assembly, the beam was quite significantly rotated. Unfortunately, I realized this only after the 3 specimens with stiffeners were tested and disassembled. For the remaining 6, the rotations at the end plates were measured. It is obvious from the results that the initial rotation of the beam had quite significant effect on the load resistance, because the rotation either added to the intended eccentricity, negative effect, or subtracted from it, positive effect. Of course, we did material tests as well. The steel was S235, and as expected, the lower yield strength was at about 300 MPa for the beam and end plate, and a bit lower for the stiffeners. For welding under load, I prescribed a specific welding sequence so that the beam cross-section is not weakened all at once, and has a time to cool down. However, I do not want to talk about it in detail now. I want to focus on the general numerical model created by Ideastatica in a joint research project. The model usually consists of one or more analyzed members, joints, and some related members. It is a multi-level model. The analyzed member is modeled whole by shell elements, the related members in joints by shell elements, and the rest by bar elements. The ends of the related members may be supported. The connections are equipped with special elements simulating the bolts and welds based on the stiffness and resistance provided by codes. The software allows three types of analysis that has to be calculated in a sequence. There is materially nonlinear analysis, linear buckling analysis, and geometrically nonlinear analysis with imperfections. This is the most advanced static structural analysis. The imperfections are introduced in a buckling mode shapes from LBA with arbitrary amplitudes. Now to the results. When calculating the resistance according to EN 1993-11, I am limited to rigid or pinned boundary conditions. For semirigid joints, the formulas for lateral-torsional buckling resistance are not provided. I have listed here all the possibilities with rigid or pinned boundary conditions. A bold engineer could use something in the middle, but the most of us are careful and would go for the resistance of about 28 kilonewtons. The inclined stiffeners restrain warping and probably help with the load resistance, but it is also not clear to what extent. Here are the experimental results. The beams without stiffeners are with dotted line. The beams with stiffeners welded prior to the tests are with solid line, and the beams with stiffeners welded under load are with dashed lines. Two of the specimens strengthened under load actually withstood the lowest load, so in this point, the design of experiment failed miserably, and the members were not strengthened but actually weakened. Welding under load increased the imperfections for beams with already high initial rotation. That is this horizontal part of the load deformation diagram. Overall, the stiffeners provided about 10% more load resistance. It is interesting to see that the specimens returned nearly to their original shape after unloading. That indicates there were little plastic deformations. To validate the model according to the experiment, the material properties, rotation and eccentricity was as measured. The amplitude of initial imperfections was chosen quite low, just 2 mm. Residual stresses were not modeled. The load deformation curves are quite close, and especially the load resistance is nearly spot on. Playing with the models allows us to perform parametric studies quickly. The amplitude of initial imperfection has of course a negative impact on the load resistance. It is interesting to note that the deflection at the peak load rises. Load eccentricity has perhaps even a more profound effect. Again, with increasing eccentricity, the load resistance decreases and the deflection at peak load rises. The same applies to the initial rotation of the beam. Note that 40 milliradiat rotation can be achieved just by standard Hall allowances, so it may not be entirely unusual. We have also compared the model with stiffeners. The resistance again depends on the initial imperfections and beam rotation. Again, the compliance is very good. However, when designing a member from the office, we do not have the measured material properties, and we do not know the imperfections in advance. So I present also the results using just the initial geometric imperfections according to the draft of the new Eurocode. With the nominal material properties, the model predicted about 70% of the average experimental load resistance. With measured material properties, about 80%. So it seems there is enough safety in the amplitude of initial imperfections. It could perhaps be considered to choose a worse buckling curve for the member with stiffeners because there were welds implied. The numerical model also provides much better insight into the behavior of the substructure. An engineer can tackle the different failure modes more effectively. I list here the results of the hand calculations again. The numerical model brings much more assurances than the wild guess the engineer must make when dealing with lateral torsional buckling of beams with semirigid joints. Compared to the safe assumption, the CBFEM model brings about 30% more resistance. To conclude, designing member together with joints brings advantages, but the traditional design methods are not ready for this. For example, lateral torsional resistance for semirigid joints is difficult to establish. CBFM model can be easily created and analyzed very fast. It shows the realistic behavior of both the member and the joints. The model was verified on several examples using hand calculations for cases with clear boundary conditions, our experiments or experiments from the literature. We also cooperate with ETH University in Zurich on verification studies, and it seems even members class 4 can be safely designed by CBFM. Using the imperfection provided in Eurocode always provides the safe estimation of the load resistance. The CBFM model is automatically generated, so it does not require deep knowledge about finite element analysis. The software is free to all students and educators. Thank you for your attention, and I would also like to express my gratitude to the Technology Agency of the Czech Republic for funding our research. Now I am looking forward to your questions.